Very good. So today we will try to conclude. So it will be more of a discussion. Let me tell you a bit of a summary and so on, and then I'll try to summarize, telling you how people now go about trying indeed to solve and to understand the ADS-CFT quantitatively by solving both sides of the duality. But let me tell that this is the last lecture, so please take advantage to derail me and ask whatever you want. And I don't have any particular goal of where to go. I don't have any notes. We will see where we go. Okay, so let me just summarize a couple of things, some of the things that we have seen. We started by studying the harmonic oscillator. We saw the energy is sum of one. One is the dispersion relation of a quanta of the harmonic oscillator. And this quanta of the harmonic oscillator obey some equations, which are the zeros of its wave function, which take this form, which we then had some fun interpreting as semi-electrostatic equilibrium position and seeing that there is some quantum version where these positions are discrete, and some classical counterpart where these positions condense into cuts and where we could understand directly starting from our classical action and doing Bohr-Sommerfeld quantization. Then we went to our Heisenberg spin chain. So we took a spin chain of spins up and down, and as a spin down propagates through this chain of spins up, the total phase acquired should be 1. This is this picture here. And this led to these famous beat equations that we wrote here, where a particle propagates around. This is exponential of the momentum of the particle. This is the energy of the particle. So if you eliminate for u, you can read what's the energy as function of the momentum, which is sine square of p over 2, the usual dispersion of a particle on a lattice. And this is the S matrix between two excitations. Again, there is a quantum version where you have a bunch of solutions, a bunch of quanta, a bunch of rapidities used. And again, you can take a sort of classical limit where you take many of these particles, they condense into some cuts. And we understood that here, the description was a classical description in terms of a low energy vector that is changing slowly along the spin chain, a low-lying excitations around the ferromagnetic spin chain. Then we went and studied, so complexity continues to increase. So we go from the harmonic oscillator, like so, to a strongly coupled quantum field theory. Okay, so from a model that we know how to solve in 100 ways to a model that naively we have no clue on how to tackle. So this was a strongly coupled model, but we could get lots of mileage just by exploring symmetries, crossing symmetry, unitarity, integrability. We put all these symmetries to our to work for us, and what we achieved was, again, we could again write the beat equations. We could find what is the dispersion relation. These particles, here is the dispersion. The momentum is m times sinh. The energy is m times cosh. You can again eliminate theta and see that here you get a relativistic dispersion. And what is this S matrix? Now I have to write first sigma and then say what sigma is, otherwise the expression will become too big because it's already starting to become kind of a beast. And we solved it in 3 different ways yesterday. How to get to this so-called dressing factor. And again here, this I did not tell you, but it's not surprising if I tell you the following. You could now repeat the same game. Take particles, take many particles, take a continuum limit. These many particles will condense into cuts, and you will get some algebraic curve. Okay? Same story as usual. What is the difference? Nothing, basically. Okay, there are some differences. If you take the log of this equation, again, what do you do? Take the log and then go and try to go again to this electrostatic picture. So you ask, okay, log of gamma functions, how are the arrows pointing? Do they point in? Do they point out? You draw a couple of pictures and you see very well that, yes, there will be some cuts again. Now the potential, here the potential is going to be cosh. Sinh is the force, the potential is cosh. It's again a box, like it was before for the harmonic oscillator. For the harmonic oscillator, it was x squared the potential. Now it's cosh. Again, some box, some cuts, and so on. And like before, we can get these cuts from a different picture. We saw that there is a nice story, a parallel story, which is the story of classical integrability, which is the idea that integrability is rooted on the idea that at the heart of it is the existence of hidden charges, mysterious charges. These hidden charges, what they are interesting because they have a very sharp physical consequence, namely that scattering factorizes. That if you bash 3 particles against each other, it just factorizes. And that's what allowed us to quantum solve the theory, right? That's what allows us to say that I take a particle, I carry it around, and I get and the phase is just a product of the phases as it meets the other particles. Otherwise, it would still be true that I take a particle and I get 1. But as the particle goes around, it scatters with everyone in a messy way. It doesn't scatter as a sequence, one after the other, after the other, after the other. What is the classical counterpart of the existence of all these charges? Is the fact that we can construct a flat connection, a connection that is flat, that depends on my fields of my Lagrangian. And on the equations of motion of my fields, this connection is flat for any complex parameter u that we call spectral parameter. And that had an important consequence, because it meant that if I wrap an holonomy of this flat connection around the cylinder, I can put this holonomy here, or here, or here, or here, and its evolution is isospectral. The eigenvalues don't depend on where I put it, and I basically generate in this way an infinite set of conserved charges. And we saw that if we think of the eigenvalues of this holonomies, so you write some holonomy, you write some matrix, and then you solve some equation to find the eigenvalues. What is the equation? It's a characteristic equation. Like, how do you find the eigenvalues of a matrix, right? Determinant of matrix minus lambda identity equal 1 equals 0. Right? So you go and you solve. But because it's an algebraic equation, of course, it will lead to Riemann surfaces with several sheets. And these Riemann surfaces with several sheets are nothing but these Riemann surfaces that came from the quantum world. So this is how we connect the classical and the quantum. Now, we saw that this was not just something esoteric with some models. In fact, it's definitely not esoteric. Here, the only SU2 spin chain that you can write is the one we wrote. So any one-dimensional material with SU2 interaction falls here. Here, it is also not very esoteric. It's the simplest model you can write, which is just a unit vector on a sphere. It's not something very tuned and so on. But it becomes even more relevant, the study of these integrable models, because we saw that in these ADS-CFT dualities that relate to theories, strings in spheres are equal to gauge theories, conformal field theories with a large number of colors. And this was implied by many arguments, such as the decoupling limit, large n, symmetries, experimental evidence. Let me tell what I mean by this experimental evidence in a second. But we had all these arguments pointing towards this nice duality between strings in n equals 4. And then we saw 2 miracles on both sides of the duality. The miracles were very simple. We went and studied what is the dilatation operator of this theory that governs the mixing of operators under Rg. And we saw that it's a spin chain Hamiltonian. That's obvious because it was just a statement of language. It was a local one. That's still trivial because it's just large n. But what was remarkable was that of all spin chains we found, the coefficients in the Hamiltonian were tuned as if someone had given us a gift. So we did not ask for it, and then we got this wonderful 1 and minus 1/2, and say, wow, this is really amazing. Of all the coefficients I could get, I got exactly the ones that make sure that the model is integrable. Then we go to string theory, and we could study the equations of motion and see, can I construct a flat connection? And the answer is again, yes. So you find these very nice miracles, that you find this integrability gift in both sides of the correspondence. And of course, if you believe ADS-CFT, you can say that one side provides evidence for the other or provides evidence for ADS-CFT and helps explain the origin of these small miracles and motivates one to look if this integrability is preserved as I go to more loops in n equals 4 or as I start incorporating worldsheet quantum effects on the string side. And by experimental evidence, I mean evidence of this sort. I mean that you find that strings are integrable, you find that very quantum strings, that is spin chains, are integrable, and you tell people, okay, please go and compute a few more loops and see if you get the right coefficients in the Hamiltonian to get integrability. Because this is what this intuition is telling me. And people go, they compute, and they find that it does. It's what I call experimental evidence, the kind of evidence that we have, which is something very common in this field. As we are making progress in trying to understand gauge theory and string theory, there is this powerful notion, which I find really very appealing, of producing experimental theoretical data, which means that you compute things, and there is this philosophy, Freddie likes to call it, is the, you know that in quantum mechanics there is this shut up and compute, and it's like shut up, compute, and contemplate. And it's very much what we do often. We compute, we look at the results, and then we try to understand what are the foundations and how do we interpret them and how do we extract deep physics about it. Okay. So remember, why did we do this detour through the 06 sigma model? The 06 sigma model was a toy model for the full string theory on ADS 5 times S5. And it was an illustration on how we could go very far with very little. Namely, the Lagrangian was very tough. What are our options? Either develop tools to deal with the Lagrangian or forget about the Lagrangian. And if the Lagrangian is tough, we don't care about the Lagrangian. And that's what we did. We basically did not care about the Lagrangian. We just used the symmetry of the particles and so on. This is not what we have been doing concerning ADS CFT. We used the Lagrangian and saw that the equations of motion were integrable and so on. In n equals 4, we used the Lagrangian and Feynman graphs to construct a spin chain and see what we got and so on. But now that we see that it works and that we see that it's integrable, can it be that we can now forget all that and go from other arguments and try to follow a geodesic, especially that we only have half an hour, we really need to follow a geodesic, and try to use really the minimal amount of information and arrive straight at the final result for what is the spectrum, the solution to the spectrum problem. Okay? So, what is this A, this E? This E can be two things. It can be the spectrum of dimensions in n equals 4, or the spectrum of string energies in string theory, or also these are the same in any CFT, the spectrum of energies if I put n equals 4 on R times S3. And it was actually this equal sign that allowed us to identify both. So this, if you want, is the simplest possible question we can ask. And then, as we said yesterday, there are other goals, which would be to compute not 2-point correlation functions, but 3-point correlation functions, Wilson loops, amplitudes, and so on. But we should probably first solve one and then ask about more complicated things. That's true. That's true, yeah. So we can add to the list. So what if we start considering, for example, a string that evolves, but then splits and joins again, so it has a hole in the middle. So this would be studying what is the first 1 over n squared correction. That's another interesting quantity. Yeah, most people say that there is evidence for non-integrability. I think there's evidence for integrability. And the evidence is very simple. It's just that if you put a hole on the surface, it's still the same worldsheet. It is still the same theory. You just decided to put it on a different topology. So if integrability is a property of excitations on top of your string, how do they scatter? Why do they care about some global issue of what topology you put them in? It looks very naive, but I think it's correct. So the problem is that it's hard to define integrability. What is integrability? Integrability is whether you are strong enough or not to solve it. So so in practice, that's the best definition. If you want to use a more another kind of definition, you can say, well, let me define integrability as the statement of whether 3 particles factorize or not. That looks more modest. Okay, it might be better, more politically correct. So let's take 3 particles, scatter them against each other, and now, does it factorize or not? If it does, it's integrability. But for example, what is 1 over n correction to this problem? It's the problem where now instead of having just single traces, you have to deal with single traces and double traces, and they all mix with each other. So now you have to change a bit your framework. You are not dealing with one spin chain, but with several spin chains, because it's several single traces. So your Hilbert space should not be the Hilbert space of a spin chain, but the Hilbert space of 1 spin chain plus 2 spin chains plus 3 spin chains in the more general setup. It's more like the Hilbert space of a condensed matter lab, where I have 1 spin chain plus lab with 2 spin chains and so on. And now what does it mean to say excitation scatter or not? I mean, I have to rephrase a little bit and think a little bit. I feel this is not useful. What's useful is to say, can you solve it or not? Or how do you rephrase integrability if your problems start to have a different topology? Good. Okay. More questions? As I said, I'm not in a rush. I can start telling things. My plan was to start making a table, recalling how we solved the ON sigma model and telling you what's the analog statement in ADS-CFT. But again, I will be very descriptive. So the first thing we did in n equals 4 in the ON sigma model was to say that a particle has a vector A that runs from 1 to n, and a dispersion relation epsilon of theta and p of theta, as can be read from the equations there. So then the first question is, what about in n equals 4? So let's first let me show you that things are a bit complicated. Not that probably this is needed. You can probably believe me immediately, but let me tell you a bit why we should expect this to be a bit complicated. So let's oversimplify here first and imagine that all we had, let's think in terms of a spin chain language, was trace of this scalar z and then this scalar z, x. So imagine this was the end of the story. If this was the end of the story, it's important to distinguish. What would be the symmetry of this spin chain? SU2, because you rotate a z into an x, a z into an x. It's SU2. Do you agree? So SU2 is the symmetry of the spin chain. What is the symmetry of the excitations that rotates excitations among themselves? It's empty. There's nothing. Excitation is just an x. There's nothing to rotate into. Right? This is what we discussed, that an SU2 spin chain has SU2 symmetry, and particles, which are these x's here, they have no degree of freedom. So in this case, a particle, there is no A. There's nothing. A particle is just a particle moving with some epsilon of p. There's no degree of freedom, right? So it's very important to distinguish this basic thing. One is the symmetry of the spin chain, one is the symmetry of the excitations, right? And you remember, if we had an SU3 spin chain, particles have SU2 symmetry because out of the 3 colors, they transform into 2 of them. Right? Sorry? It's just X. U1, but if by U1 you mean that there is conservation of number of X's, it's true. But it's not a symmetry. It's a symmetry that measures how many particles you have. So what you are saying is that I can measure how many particles by acting with a symmetry that takes out exponential of a phase that counts how many x's I have, right? But it just counts how many x's I have. It's not a symmetry that is rotating particles among themselves. That's a symmetry that is telling me the number of particles is conserved, right? It's like saying that I have a bunch of particles. They have no degrees of freedom, but they have charge. That's fine. So that means that if I put 4 units of charge, I get 4 units of charge. I cannot get 5 units of charge by evolution. Okay, so now, but this is a simplification. But in reality, things are more complicated. Let's see how complicated they are. So first, we can have an x. That's fine. But further down, we can have a y, and so on. So we can already have 2 scalars. Okay. In fact, you remember there are 6 scalars in n equals 4. And we can construct linear combinations, which is useful to give them charge, because once you give them charge, they are conserved, and you cannot change their number, so that's why it's quite convenient. We introduce z to be phi 1 plus I phi 2, x to be phi 3 plus I phi 4, y to be phi 5 plus I phi 6, and then their complex conjugate fields. So further down the spin chain, I can also put a y bar. Or I could put also an x bar. Okay? So you would say that particles, there are already 1, 2, 3, 4 kinds of particles. But you could say, well, I can also put a z bar. Okay? Is it okay? But here comes the first important thing. This z bar, I want to claim now the following. That these guys here, these are all excitations. But this one is not. This is unstable. This is one step. So how do we see it very easily? We see it very easily because what happens if I act with my Hamiltonian here? Under the Hamiltonian, if I act with the Hamiltonian, what happens is that this y bar moves on the spin chain. I act with identity or permutation, and the y bar is just moving along the spin chain. Right? But what happens if I act with Hamiltonian on a pair ZZ bar? Remember that if I act with the Hamiltonian on ZZ, I get 0 because identity does nothing, permutation does nothing, and trace does nothing. Remember why trace does nothing? Because it's phi 1 plus I phi 2 times phi 1 plus I phi 2, and there is phi 1 minus phi 2 phi 2. But here, because we have ZZ bar, there is no this minus, there's no cancellation. So what happens when I act with Hamiltonian on ZZ bar is that I produce a lot of particles. X bar plus x bar x plus y bar plus y bar y plus z bar and z bar z. So in fact, the proper way to think about this is that if I put this z bar and now start evolving, this z bar is not neutral with respect to the vacuum. It's like radioactive. So it immediately decays into an x and an x bar, and then the x and the x bar start moving and they go far away. So in other words, we have an x, and the x is moving, and the x bar is moving, and then there is here an explosion region where the wave function is complicated. In this explosion region, here we find z bars if we would look inside. But if we consider a scattering experiment, we should not think of z bars as being an asymptotic state. Z bar is something that along the spin chain can be produced if I hit an x and an x bar, or a y and a y bar, but it's not an asymptotic excitation. Okay? Well, then it means that we have 1, 2, 3, 4. So, for example, concerning scalars, if we just focus on scalars, we have SO4 symmetry for the excitations. Right? Let's go on because we can put more stuff. Now we could imagine on my spin chain putting derivatives. Okay? And here we have something similar. We can put one derivative. We could also put two derivatives. Right? We can put two derivatives. How do we think about this? It's the same story. Two derivatives is not a new excitation. Two derivatives is what you get if you have one derivative moving, and when they are on the same position, it's two derivatives. But then they just continue. In other words, derivatives are also excitations, but contrary to the scalars, they are not hardcore bosons. They don't mind being on top of each other. You can have three of these derivatives coming in and making a tower of three derivatives. Okay, so this again, this is an excitation. This is not. Then you ask, do they move together? Or when I start acting with the Hamiltonian, which I did not write for the derivatives, or do I act with two derivatives and does it split into one derivative on each side and then the derivatives go their merry ways? And it's the second way. Right? So you have to, I did not show you how the Hamiltonian acts mix. So there will be an Hamiltonian, like there is an Hamiltonian that mixes the scalars. There is an Hamiltonian that mixes the most general field configuration that we did not write. We did not have time to do everything, right? In particular, you could see that what this Hamiltonian does is when it acts on two neighboring sites, this one has n derivatives. This one has n2 derivatives. It reorganizes the derivatives such that the total sum is still the same, but reshuffles them. In particular, if you put 2 and nothing, and you act, it puts, there is a term which has 1 and 1. And then if you act on the neighbors, this 1 and 1 moves. And now they are far away and they don't talk to each other anymore. And now they just propagate. Okay? A d mu and an x, I would think of it as having an x flying far away, a derivative flying far away, and there is a point where they can be on top of each other, but then they go. Again, this is the same story. You can ask, if I have a derivative and an x, do they move together or do they just dissolve? And they again just pass by each other. X and x bar are different particles. So now that I see that there are 4, I can go back. You see, I'm saying that I have excitations which are made out of these 2 fields and their complex conjugates. So now if it's these 2 and their complex conjugates, I can very well go back to this real notation and say that now I have excitation phi 3, phi 4, phi 5, and phi 6 that transform under SO4. So then we see that then we have the derivatives. Okay? And the derivatives, they transform under which group? Under Lorentz. Right? There is the index mu, and they transform under Lorentz. Yes?
So going back to the Z bars, you said that Z bar is unstable, but when it decays, one of the products is another Z bar, right? So we're never going to get rid of Z bars.
You are. Okay, you are complaining that here there's also a ZZ bar. So then let me put as an exercise that if you put a Z bar and act with the Hamiltonian, you will see that it will decay into an X and an X bar. I mean, this is very naive. I have to exponentiate, act with the Hamiltonian, do it properly. I mean, the physical picture should be clear, no? I have X's and X bars that move. If they are close to each other, they have the quantum numbers of a singlet, which is XX bar. So that singlet can produce XX bar, YY bar, ZZ bar, and so on. But then they just continue moving. So you can have, for example, a scattering of an XX bar producing a YY bar. But an XX bar cannot produce just a Z bar. Where would momentum go? Good. That's absolutely true. That's absolutely true. That's important. Okay, good. Perhaps I should emphasize this. The way we are solving it is to make our life easy. We are picking a vacuum, right? So it's very important that we define this as being our vacuum. And in fact, there are other vacuum descriptions of the theory. This is the simplest one, actually. It's the one that makes contact with the ferromagnetic limit of spin chains, the one we studied in the lecture. But you could imagine, why don't I start over a totally different vacuum, a vacuum of just, for example, product of many field strengths. So it would be a totally different vacuum. And then I would have to repeat my analysis of who is excitation and who is not excitation. So let's go on. So we already have scalars, derivatives. And I remind you that SO4, that both these groups, I mean, then you have to define the real forms and so on, but they are basically a bunch of SU2s, right? SO4, SO3, 1. Lorentz is just SU2 times SU2, right? You can write Lorentz index, an index mu, you can put it in spinor-realisticity with alpha, alpha dot. Is it clear? You remember? So Lorentz, representation of Lorentz are parameterized by a J1 and a J2 of SU2 times SU2. Right? So we see that the symmetry group is not SU2. It contains a bunch of SU2s. So far, 4 SU2s. And then there are the fermions. So we continue. It's more complicated even. There are the fermions. The fermions, once you reduce them from 10 dimensions to 4 dimensions, they end up with indices of R charge and indices of Lorentz. And there are fermions with up index of R charge and dotted index of Lorentz. Okay. So these dotted indices are the indices of Lorentz. The right and the left SU2. So these are the spinor indices of my fermions. And this A is an index under the internal symmetry, which is called R charge, R symmetry. Remember the scalars, they are 6 scalars that rotate under this symmetry, right? So this is an SO6 symmetry. Do you agree? SO6 is the same as SU4. So your matter must transform under representations of SO6, but you can have part of the matter transform in a vector, like the scalars. And in fact, what happens is that the fermions transform in the fundamental of SU4. So this index A transforms in the fundamental of SU4 which is the same as SO6. And the A is in the 4 bar, in the anti-fundamental. So these are the fermions. And you see that the indices rotate independently, the SU4 and the Lorentz index, the two Lorentz indices rotate individually, so it's easy to see that what these fermions do, they kind of complete this bosonic group in a simple way into what are called a supergroup. Okay? So let me write what the result is, but it's actually going to be a bit incomplete because you will probably not know what the notation means. But I just wanted to point out that now if you add the fermions, what you get is SU2/2 square times an important detail that I will come back later. Okay? So this is the symmetry. If you want, you have the symmetry of the theory, the full symmetry, all the supersymmetry that rotates fermions to scalars, all the R symmetry that rotates the scalars between themselves, Lorentz that rotates derivatives between themselves. And you ask, what is the residual symmetry that kills the vacuum and rotates excitations among themselves? And this is the answer. It's an SU2/2 square. Now, the only thing I want to point out here is that, okay, morally speaking, this is like, 2 + 2 is 4. It's like SU4 square, morally speaking. It's a compact group. There is a finite number of excitations, 8 scalars, 8 bosons. And you have a symmetry that rotates these 8 scalars and 8 bosons among themselves. Okay? Is it clear? So you have 8 scalars, which are 4 here and 4 here. And you have 8 fermions. And this SU2/2 symmetry is a symmetry that rotates these 8 scalars and 8 fermions among themselves. Okay? So this is what this SU2/2 symmetry is. This SU2/2 symmetry it's a symmetry that rotates. We have 8 bosons plus 8 fermions. These 8 being 4 derivatives plus 4 scalars, the ones that are excitations. And they are rotated. There are all these symmetries that rotate among themselves by this group SU2/2 square. And what I want to emphasize, it's a compact group. Of course, it rotates this finite dimensional set of fields amongst themselves. Okay? And I just want to contrast this with the starting point, which is clearly a non-compact group. Even Lorentz inside is non-compact. Right? Lorentz is a non-compact group. So this is much smaller. I don't know how you do much smaller in the sense of groups, but how do you say? I don't even know contained. A group is contained in the other. Is it like this or like this? I want to say this is contained in the symmetry group of the spin chain. Is this correct or it's the opposite? It's correct? Very good. And very contained when it's much smaller. Can I put like this? Does it exist? So this is very contained in the full symmetry group of the spin chain. Sorry? Sorry?
Derivatives transform under SO1,3, so that's still non-compact.
The derivatives are, the group is non-compact, but there are 4 derivatives, and there is a compact group that rotates the derivatives among themselves, which is SU2 times SU2. It's a non-unitary representation, if you want. Let me explain in 1 second. I think it will, you will be happy with what I'm going to say. What is the full symmetry group of this spin chain? It also has a name that it probably will not tell you much, but it's PSU2,2/4. Okay? In the same way that this was roughly SU2 times SU2, this is SU2,2 times SU4. SU4 is SO6, we understood, and SU2,2 is SO2,4, which is the full conformal group. Okay? So this spin chain here, it's a non-compact spin chain. It's an infinite dimensional representation. Why? Because you can at a spin chain site. So if this is a spin chain site, here I can put any scalar, z, x, y, z bar, and so on. So for example, I can put 6 scalars. This is the SU4 here that I can put any scalar, right, as we discussed. But from the point of view of derivatives, and this is what you are saying, I can put 1 derivative, 2 derivatives, 3 derivatives, and so on. And it must transform in a representation that rotates all this infinite dimensional space into each other. This is the representation of the spin chain, which is a infinite dimensional and therefore unitary representation of SO3, 1. It's the representation that rotates, that moves you inside the space of putting one derivative, putting two derivatives, putting three derivatives, and so on. The representation that we are dealing with when we deal with asymptotic particles is different. We can just have one derivative. Two derivatives is already not an excitation. And we just have one derivative or one scalar or one fermion. But that's it. And they move and they scatter with each other. So from the point of view of this rotation, you don't see this non-compactness because there's now only a finite set of them. Okay? So you see that because of this infinite, this is, and then there are fermions. So this is a super, because there are fermions, but also non-compact spin chain. This already makes it hard. It's supersymmetric. It's non-compact. It's kind of a complicated spin chain where you have a complicated Hilbert space at each point. With long-range interactions at higher loops. As you remember, the idea is that we have a spin chain Hamiltonian. At one loop, it's nearest neighbor. At two loops, it's next to nearest neighbors, and so on, and the range becomes bigger. So trying to study this beast right on, it's very complicated, because you have an infinite dimensional Hilbert space, an uncompact spin chain, the range starts growing and growing and growing. It's kind of a complicated beast to try to parameterize it completely. So that's why this language here, you see, the language here, which is the language, if you start with your Lagrangian, right? If you follow what we did, this is the language where we go. This is step number 1. And typically what we will do is first we do step number 1, find the Hamiltonian. Then start putting excitations on the spin chain and scattering and so on. And then as a step 2, we will go to the S matrix. What we are trying to do is shortcut this and go directly here. And now you see we have good reasons to do it. Instead of dealing with infinite dimensional non-compact spin chains with all this complicated symmetry, we are dealing with a simple spin chain where we scatter an index A that runs from 1 to 16 if you want this, all these 16 excitations. And we just have an S matrix with some S, A, B, C, D. How much simpler it is? It is just 256 times 256 matrix, right? What is this compared with all possible long-range spin chains which are non-compact with this non-compact group and so on? That's much simpler. Okay?
What is the consequence of the compactness? Do we use it from there?
It's that it's just 256 by 256 instead of infinite by infinite. It's much smaller. It's a bit better, but it's true.
Even if you just work at the level of Lie algebra, then also it would be just 256. So you don't need to make the statement that the group is compact, and you're dealing with a non-unitary representation of a compact group.
The symmetry group that now rotates these excitations as they are is embedded into this non-compact group, but is a compact group. It's not just that the representation is finite dimensional. This is the symmetry group of the excitations. The symmetry group of the excitations and the symmetry group of the original theory don't need to be the same. Right? The scalars was the simplest example. The symmetry was SO6, but the symmetry of my excitation is SO4. Right? The derivatives, it's similar. The symmetry that is relevant for the derivatives, it is now just SU2 times SU2. It is not the non-compact version of it. It really is, because you just have a derivative D, which has an index alpha and alpha dot. And what is the symmetry? It's just what rotates the alpha and what rotates the alpha dot. So it's really SU2 times SU2. I'm not hiding anything. So it's what it is. It's a compact group that just rotates these 4 derivatives among themselves. Right? Okay, good. So we answered the analog of this question. See? So already a bit non-trivial. But this index A is an index that runs from 1 to 16. Right? So we answer this question. So we have a particle, and there is an index A that runs from 1 to 16. Or it's actually more useful to consider A as a product of two indices, each of them running from 1 to 4. Because if the symmetry group is SU2/2 times SU2/2, I can use one like we did for the derivative, d alpha alpha dot. It's more useful to use one index for the left part, one index for the right part. Then the S matrix actually simplifies. The S matrix then will become an S matrix with indices A, B, C, D times the other indices A dot, B dot, C dot, D dot. So now instead of 256 by 256, it's just 16 by 16. Okay. This is reasonable already. So each of them is a 16 times 16 matrix. Okay. Now, we did not, actually, I said we solved it, we didn't. Because what about epsilon and p? What about the dispersion relation? So what we answered was the point about what is this index A. Okay. Well, we did not answer. I told you what the answer is. There is, of course, work to arrive at this and to make sure everything is cleaned up. But I tried to argue. So what about now the dispersion relation? What about epsilon of p? Okay? And here is where things in EDS-CFT and in this particular model are different from the conventional case, which is symmetry is really super powerful. It's much, much more powerful than usual, and it's related in this important detail that I hid there. And the point is that in the symmetry algebra of, we have the symmetry algebra of n equals 4 super Young mills that rotates the scalars, rotates everyone amongst themselves, and so on. But you see that there's something funny, that inside the algebra, one of the elements of the algebra, of this symmetry of this theory, is the generators. The generators are the generators of the conformal group, right? And in particular, the dilatation operator is inside the algebra. So there is this funny thing that the dilatation operator is one of the elements of the algebra of my symmetry group. Okay? Is it clear? So what happens is therefore that the symmetry and the dispersion relation, they are actually not totally independent. And just by symmetry, we can, so for example, let me remind you that we have relations of the sort. Who here saw supersymmetry? Almost none? You did not see supersymmetry in explorations in particle physics or something like that? You saw a little bit at least, right? Sorry? They don't have to take? But in, okay. So let me tell, in supersymmetry, there are symmetry generators that people call Q, and if the theory is superconformal, there are other ones that you call S. So these are SUSY generators. So it's just a statement, but okay. So they rotate. These are the ones we use to rotate. We act with a Q on a scalar, we get a fermion, and so on. And when we rotate them into each other, we get stuff like R. R is the R symmetry that rotates scalars amongst themselves, the symmetry that rotates the scalars amongst themselves. We would get L. L would be Lorentz. And we would get D, where D is our spin chain Hamiltonian, is the dilatation operator. Okay? So what typically happens is that you start acting with your symmetry generators, and there are two things you can use with this. You can either use it to rotate amongst your particles, or you can apply twice and construct the anticommutator on the left and use it to measure the energy of the state. Because you act on a fermion, it goes to a scalar. You act on the scalar, it goes back to the fermion. But after it goes back, it doesn't go back with coefficient 1, but with coefficient out of which you can read off the energy of the state. Okay? So that's the basic idea, that the algebra and the Hamiltonian, now they are interconnected. Okay? So again, to summarize, I take some state, there are some excitations, and I can, with the symmetry tells me not only how to rotate, but if I try to use supersymmetry and apply Q followed by S, which would basically take phi, go to psi, psi goes to phi again, it does go back. I start with a boson, I end up with a boson. But in the process, I can also read off the energy of my excitations. Okay? But then you could be a bit puzzled because you could say, okay, so you have some algebra. This algebra will be some kind of simple Lie algebra with a bunch of coefficients. I did not put the coefficients. Perhaps there are some 1/2 or something. This algebra is constrained because you will have Jacobi identities. And you will just apply this algebra, measure the energy. How are we going to get non-trivial functions of momenta? I mean, you are going to tell me whatever you will do, you'll perhaps get that the energy is 1 or 1/2. How are we going to start getting information about the momenta of the excitations? So even without giving you any details, is it clear that this naively sounds like a bit of a puzzle? So we have some algebra, like SU2, like sigma x, sigma y is 2 sigma z. Whatever I start doing with this algebra and commuting and so on, how can I start getting energies, dispersion relations like we got there for the magnons, which has momentum and so on? Okay? So a priori, you could be confused. You could say, is it really, you could ask, is this really the Hamiltonian, or is it perhaps just the classical dimension of the operators? You could ask, are you sure it's not just the classical dimension of the operators that you measure and so on? And indeed, if you do it naively, it is just a classical one. But if you do it properly, you get the full Hamiltonian. So what does it mean? It means that the symmetry stuff is a bit subtle. And what happens is that actually the symmetry, this tensor with an important detail, is tensored with gauge transformations. So when you apply a symmetry transformation, you could get a scalar goes to a fermion plus a gauge transformation, because gauge transformations, you don't care. It's just a gauge transformation. Okay? Now, when you do it, and I try to ask, okay, this gauge transformation acting on the full state should not matter. But can it be that acting on the constituents of the spin chain, that it does matter? Okay? And this is precisely what happens. So instead of trying to give you a very vague discussion, let me try to tell you a little bit what I mean by this. What I mean by this is the following. You start studying your algebra, and you would get that Q times Q, okay, acting on a field phi on one of the scalars, where this scalar would be one of the excitations, so it can be 3 up to 6, 3, 4, 5, or 6, one of these SO4 scalars. And if we follow what it gives, you say that this is not equal to 0. 0 would be the naive result that you would do if you would just try to close the algebra. But in fact, it's equal to a gauge transformation. It would be equal to something like G squared times the commutator of a scalar with a Z field. So it's some funny operation where you insert a scalar Z. So it's like you have your vacuum, and you put some excitation, and your symmetry, it's almost trivial, but it changes a bit the length of your spin chain. It adds a bit of Z. Now, this normally you would not care, because remember, if you have a trace of a product of fields, chi1 up to chi L, and if you change each chi going to chi plus the commutator of chi with some parameter, whatever parameter it is, it drops out of the trace. So if I apply this transformation to everyone, it just disappears. It's just a gauge transformation. But we can think, because of the trace, because of cyclicity of the trace, this is just the infinitesimal version of conjugating the field, which we saw. We put the trace such that this conjugation doesn't matter. But what we are thinking is not of a closed chain, but as an open chain, right? Because we are describing a single excitation on an infinite vacuum. That's what we are discussing now. So we are kind of decompactifying, thinking of a single excitation, and later we will compactify back. So what we will say is that this should have a trivial effect, on the full state. That's true. That's definitely true. But perhaps we can relax the condition that it is trivial on fundamental excitation. This is totally legit. But perhaps not on individual excitations. But then it becomes something quite interesting, because then you can start acting with your symmetry generators on spin chain states where you have magnons moving around. So let's suppose a magnon is moving around. So we have a magnon moving around. Let's use this notation where we have e to the I momentum times n. And then we have all our spins up, and here is our scalar, which is a spin down. Right? And we sum over n. And now we act with these supersymmetry transformations. So what happens is that after acting with these supersymmetry transformations, what do we get? We change the ket, which is at position n, which we change it by this commutator. So it gets changed to g square times sum, g square is lambda. Tooth coupling. Sometimes I use g square. It goes to lambda times sum n over 1 e to the I pn, and then I either do nothing, which is the same thing, or the commutator has another term minus a term where the excitation is now at position n plus 1. Okay? But now you can, it's very easy here, you just reshift n. So you get that this is equal to lambda times 1 minus e, I add and subtract 1, minus ip times the same state, times the state again. Okay? So many people seem puzzled. So let me conclude what's the summary of this esoteric thing, and then you will ask questions. So the conclusion is that something funny happened. This anti-commutator, that if you open Wessenberger and so on and try to study the supersymmetry, you naively think it's zero. It's not exactly zero. It's more like a gauge transformation. This looks like something very fancy. But what's the net effect at the level of my SU2/2 algebra? I'm saying that it gives something here, which is not zero. But that something just acts on my state, giving a number times the state. So this is a number. Now a number commutes with all the elements of the algebra. So this is what people call a central extension. It's an extension of the algebra by something people call central, because it's something that now commutes with everyone else. So what we get is actually SU2/2 square tensored with a central extension. And this central extension, which came originally from the fact that we are dealing with the gauge theory, is what is injecting inside my algebra momentum, uncoupling. And now when I study Jacobi and impose that everything closes and so on, and then at the end go and measure D, I can measure the energy of my state. Okay? What do we find? Now we can derive, just based on symmetry, there is some work, and let me tell you what the result is. It is just square root of 1 plus lambda over pi sine square of p over 2.
I'm a bit puzzled by the appearance of lambda there. Somehow this is not a classical effect, but
it's a quantum effect. Yeah.
One loop renormalization.
Whatever I would say, strictly speaking, I would not sleep well at night because it will be a bit incorrect. Yeah, it's kind of a one loop effect. You can see that the action contains this commutator of scalars. So it's not so surprising if I tell you that to close a supersymmetry algebra, you might need to produce commutator of scalars to cancel when you plug it into the variation of the action. That is true. And because it's a vertex, it contains a g square compared to the kinetic terms if you normalize properly. So I could explain that, and then I would not invoke one loop effects. One loop effects, you start having to evoke them because this is a funny gauge transformation, which is change. Now you see, the spin chain It's actually even more complicated. It's a super non-compact spin chain with long-range interaction and which changes size as we act with Hamiltonian, sometimes by a little bit. You can sometimes change a little bit the size of the spin chain by 1. So it's really a kind of a funny spin chain. But the fact that it changes sign, it increases a little bit, you could say perhaps it should also reduce a little bit. And indeed, if you go to the conjugate of Q, which is S, it has the effect of being a gauge transformation with a Z minus 1. And the Z minus 1 is the effect of removing a Z. And that's a bit strange. I mean, to derive that, then you would say, either I just say it should be the conjugate of this, and therefore it should be that, but perhaps it can be derived by a loop computation, but no one did it. Instead, the way people originally derived it, and this was the work of Bizert, he just said, look, if I take the algebra as it is, we are going to get just classical dimensions. We need to do something to this algebra. This algebra is too restrictive. If I just have integer numbers in all the coefficients, I'll start commuting my stuff, I'll get some integers. What can I do? I need to extend it. But algebras are very restrictive. I cannot just say, oh, I'll put here some other generator. Then everything falls down. Jacobi falls down. It's a disaster. So what is the minimal extension of SU2? So first, most superalgebras don't admit extensions. It's really very rare if it admits. And SU2/2 is a special one that does admit a central extension. So then he said, let's try to centrally extend. And then, as you centrally extend, then you can go on and you find this result, and then this result you become very happy. Because now we look at this result and see this is what we were looking for. It's something that is not a spin chain and is not a sigma model, but it interpolates between the two limits that we found before. If we take lambda small, it becomes just our lambda over 2 pi sine square of p over 2 plus dot 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 at lambda very small. When lambda is very large, if lambda is very large, you should also rescale p to go to p over square root lambda. And you get just square root of 1 plus p squared, which is the relativistic energy of the energy of relativistic excitations. So it's kind of a fun dispersion relation. See, it has a square root, like relativistic particles, but it has a sign, like lattice models. It's something a bit in between the two. And this is the full exact dispersion relation of excitations of ADS-CFT. Okay? So now we can draw, really, our blob with a particle. We know this index A. This index A transforms under SU2/2 square. And epsilon of P, we know what it is. Yes?
Can I ask you, like, these two Qs that we on the right hand side of the so is that two different generators of solution?
Yeah, there are Qs and there are S's. I'm not giving you many details. Yeah, there are Qs and there are S's.
Why would we naively think that the commutator would not be 0?
No. 0 is the naive one. No, the naive is pointing to the 0, not to the not equal. Normally, we would think it should be 0 because we would have nothing to write here on the right-hand side. There's no operator with the right quantum numbers that you would write. Here we have a central extension. It's not an operator, it's just a number. Okay. The point is that each of these guys has dimension 1/2. So this has total dimension 1, and if you see with these quantum numbers, there's nothing you can add. So what is the way out? The way out is that this is not rotating you amongst the fields phi and psi, but it's putting an extra z. And because you put an extra z, the z has dimension 1. So that's how you can suddenly put something on the right-hand side. So you can put something on the right-hand side because you have this, you are in this decompactified limit where if dimensions don't work out, you say, oh, it doesn't matter, I put an extra z. The spin chain is infinite anyway, who cares? And if you need to remove a dimension, you say, oh, I just remove a z. Then I fix the dimension. And because you are in this decompactified infinite spin chain, you can do it. So this allows you to extend a little bit the algebra. You go to this central extension where you just multiply by this number, and this injects P into the Jacobi identity and everything related to the algebra. And then closure fixes completely the dispersion relation. You see? Okay, so this is the very, very, very basic first step, step 1. Then there is step 2 of trying to bootstrap the S matrix. Now, this is a 16 by 16 matrix, or 256 times 256 if you put everything together. And you might think that this is very hard, and it is definitely very hard. And you might think that it is going to follow along the same lines of the SON sigma model, namely, First, we write everything with the proper tensors. We have A, B, C, D. We just put all possible tensors and so on. Okay? Then you impose Young-Baxter to fix the coefficient of the different tensors, like we did before. But actually, here things are even better, and something quite remarkable happens, which is that supersymmetry alone, because this superalgebra, closure of the, if you impose that S matrix is invariant under the superalgebra, the bosonic part just tells you that you should put the indices properly. That if you put an SU2, two SU2 indices, you must contract them with some epsilon alpha beta or something like this. You cannot write things that don't make sense concerning indices. But then you ask, what about the super part? So you have two particles, you start acting with supersymmetries, and sometimes you start producing these Z's. But these Z's you need to carry to put them, to reshift the summation of the second particle. So it becomes, you start getting relations between the different elements of the S matrix that the bosonic part could not constrain. And amazingly, just using symmetry, so just imposing that the S matrix commutes with all generators of SU2/2. This is what symmetry means. Just this, without any Young-Baxter, this fixes the S matrix to be equal to some matrix part times some function sigma of U1, U2. This function you cannot fix at this point. But the full matrix structure is fixed just by symmetry. Okay? This is, I mean, you should have in mind that this is super powerful because imposing symmetry is a linear operation. It is just commutator of S matrix with something is equal to, it's a linear thing. So it's very easy to impose symmetry. You just write a bunch of linear equations and you solve linear equations. Super simple. Solving Young-Baxter is product of three objects. So it's a cubic matrix equation. It's much, much, much more complicated. But then you start sweating because you find this S matrix purely based on symmetry. So now you ask, what if now Young-Baxter fails? Because I have nothing to tune now, right? So now you are going to check Young-Baxter, you are trembling before clicking Shift-Enter, right? You are really scared. Now everything is going to fail. I'm going to disprove ADS-TFT. It's going to be a disaster. Then you go, and luckily Young-Baxter works. Okay? You plug it, and Young-Baxter works. And then you can show more mathematically rigorously from group theory why it had to work. But when Beiser first found out, I think it was really a relief that, okay, and then Young-Baxter works. Okay? Which is good. And then we go and try to fix this sigma of U and V, U1 and U2. Now, how do we fix it? Well, same story as before. We produce now a particle, an antiparticle pair. So the idea will be as we did for the sigma model. The idea now is consider again a particle, single particle pair which is spurious, which is killed by all symmetry generators. Like for the SO6, it was the sum over all possible colors, this singlet. And we fix the energy, we fix this rapidity, P1 and P2, such that one is minus the energy of the other. Okay? And we impose that scattering past this object is equal to no scattering at all. And this will give an equation of sigma UV times sigma UV equal to something explicit. Right, which comes from the matrix part, where here I have to fix something. So this is the original S matrix, and this is the S matrix when I cross my particle to become an antiparticle. Okay? Then you take this sigma, and you solve this equation. But here, of course, we have to remind, how do we solve this equation? Lots of physics goes into it. We saw for the SO6 model. In fact, typically, in solving these classic equations, there is the complicated function, like these gammas, which is the easy part, because you just find one solution. And then there is the easy function, which is the tangent, which is the hard part, which requires thinking a little bit more subtly about the physics and understanding the zero modes of this equation. Okay? And you can, and you find, and you solve this equation, and you find this sigma. Okay? Once you solve this sigma, you can now write the equations. E to the I, momentum times length times product of S matrix equal to 1. and the energy is sum over epsilon. Except that this is wrong. It's wrong in the sense that if the spin chains are not very big, if your operators are not very big, many of the arguments we said, like we take separated particles, we scatter them, and so on, of course, we cannot, strictly speaking, use them. So then we have this box plus corrections if for small operators. Okay? So if you are interested, I can tell you what this sigma is, just so that you see how it is. It's a bunch of gamma functions also, but it's richer, it's more complicated. But I will, if someone wants, ask me, and I'll show you at the end of the lecture. But now let me just end with a few comments, a few general comments. So first of all, I think in the end, it's very exciting that this is possible, because now we solve this, we have these predictions, and now we can solve these equations and compute the energy of states up to 5 loops, for example. We solve these equations in 5 loops, and then we tell people in perturbation theory, I got this. Can you compute, please, and check if you get this? Of course, it's much tougher to do Feynman diagrams. Doing a one-loop Feynman diagram is probably harder than doing all this, once you know already how to do all this, of course. But then people go and they check, and there were numerous checks of these final equations. Many checks you can do. You can do very interesting checks, like, for example, taking many particles here, getting some continuous limit of these equations, getting again some algebraic curve, and comparing with the algebraic curve that you get from the full supersymmetric sigma model. Doing the kind of checks I was doing there at the end that we did for simplified models. So there is a vast amount of things that could be said about the amount of checks that could be done. But I just want to emphasize that the way we presented it, because typically that's what happens in physics, large strings or large operators is what we typically care. Say in condensed matter, we don't typically care about a spin chain with 20 sides. We want to consider a big macroscopic spin chain. But I just want to emphasize something obvious, which is that this small detail, the fact that in principle we need to start correcting as we have small operators, is not a small detail, and it's something important. So, and the reason is obvious, of course. In the end of the day, what we have right now, we don't want to compute the correlation function of an operator with 23,000 z's, and then an x, and then a bunch of z's, and another x, with another similar operator. I mean, this is not the most natural observable in our quantum field theory, right? I don't want to consider this. Actually, for example, if you consider such operator, you can use this box. The box is good, plus some order up to some lambda, which will be like 200, 3, 5, 6, 1. So you see, you can go up to 23,000 loops. You could trust this, which would be look good, it would look impressive, but who would care about such operators with 20,000 fields? What we want instead is something more reasonable, like what's the commutator of trace of zx squared with trace of zx squared. We want to know the lightest ones. These are much lighter than these ones, much smaller dimensions. So in the end, what we want basically is we start with an infinite particle moving. Then we went to a circle which is big. But in the end, we want to go to a small circle and consider an integrable model in a small circle. This is one more step. It's not the most complicated one, and there are techniques to do it. Let me just tell you what the basic idea is. And the basic idea is to exchange time and space. The basic idea is to say, you want a small circle, so a small circle looks tricky because there's not much space to move, and I cannot use bit equations. But that's fine. Suppose we are doing some path integral. There is a lot of space to move if I think of time. So instead of thinking of time evolving like this, let's think that time evolves like this. And let me consider instead that my excitations are moving here. And I do the path integral from the opposite direction. So this, you see, this picture leads to the following statement, for example. That if you consider this direction to be huge, right? Then what, and this direction here, which is what we want, L to be small. Then if we think from this point of view, if the direction is very huge, we project into the ground state. So on the one hand, this is given by e to the minus beta times the ground state energy at length L. Right? On the other hand, if we think of this from this point of view, this is equal to e to the minus the length times the free energy per unit length at inverse temperature L, which is the periodicity that we identify. So we conclude that this looks impossible to achieve because the length is small. I have no clue what to do. But this looks very easy. It is just put the system in infinite volume, right? And this thing we can do very well. This we will adjust integral over all solutions of beta equations e to the minus beta times the energy of the solutions in infinite volume. Right? This we can in principle do. We know beta equations. If the length is very big, we can sum over all solutions. We sum over all solutions, compute its thermodynamics by summing over how many solutions there are of those equations and so on. You see, it can be a bit complicated, but it's a priori well-posed problem. And you study its thermodynamics, and you can get information about finite sizes. So there are a couple of steps that we will have to find the gap, but it is possible also to go to finite circles. So in the end, right now, it is possible to just take an operator and plot what happens to its energy as you change lambda. And you can really see operators going from a gauge theory to a string theory. And you can really follow them and plot these curves and see that they go where they should go at strong coupling, they start where they should start at weak coupling, and study for the first time the full interpolation, full plots of a strongly coupled theory, of a strongly interacting gauge theory. And in the end, what we want to do is to be able not to put on this vertical axis the spectrum, but to be able to put anything. We want to be able to do all possible plots, correlation functions, Wilson loops, scattering amplitudes at any value of the coupling. And thus understand the emergence of strings from gauge theory and understand how string theory emerges out of gluons, how the degrees of freedom normalize. And what we have is a laboratory, not only to understand more about how to compute in a very efficient way in gauge theory and string theory, but it is also the right framework for asking very deep questions, such as how does strings emerge, how does space-time emerge, how do we see this holographic direction that was not there in the beginning, there was only 4 dimensions, how does these holographic directions emerge, and so on and so forth. And by having this kind of guiding principle from ADS-CFT of helping us, giving us numerous hints about how the result look like, we are in a great shape, and I think we are living exciting times in physics where we are going to solve for the very first time a strongly coupled string theory or a strongly coupled quantum field theory. And the hope for many of us is that this would be a bit like the Pandora box, that once one quantum field theory is solved, that great things should happen. A bit like when people solved for the first time the two-dimensionalizing model. When people, I mean, if you see what, at the time before solving the two-dimensionalizing model, people did not even know if phase transitions existed. Some people will think, oh, when we will find an exact solution, we'll see it smoothened out and so on. So there are very, very fundamental things that we now understand about physics, that the Ising model was really a huge Pandora box. And now we understand very well two-dimensional statistical models. They are not a big monster. They are under control. After the Ising model came the Potts model, many other models, conformal field theory, critical phenomena, all these fields, integrability. They came out of an explosion, basically, highly directly consequence or highly boosted by the existence of this exactly solvable model. So this is one aspect of ADS-CFT. One very promising aspect I find is understanding more about what really string theory and quantum field theory is about by really understanding this particular solution in all possible detail. But even this thing, which I think is highly ambitious, is only part of the big grand scheme of things, where ADS-CFT has many other applications, as we saw, as defining gauge theory, defining string theory, being a useful computational tool, helping us prepare many Gedanken experiments, telling us about information paradoxes, strongly coupled dynamics of black holes, fluids, and whatnot. And my hope is that, okay, we try to follow kind of a geodesic towards a point which is more or less at the border of human knowledge. But now I hope that you will now continue to explore. And in particular, this last homework, I prepared it in a way that I gave you a few topics. Each of these topics could have been one more lecture. If we had more lectures, for example, I could tell you about this trick in more detail. This is the so-called thermodynamic Witten-Satz, how you put system finite volume. So I ask you, prepare a lecture about this thermodynamic Witten-Satz. Or I could tell you, for example, when we take this and we say that we pick a particle and scatter it and get just this simple bit equation. This is an oversimplification, because if particles have degrees of freedom, each of these crosses is a matrix, not a number. So this is what's called the nested Witten-Satz, what happens when we increase degrees of freedom. We never derived these equations, even for the spin chain. We just argued, and I told you. So it would be nice to have one derivation of the equations where we see these bit equations derived. That's another point of this exercise. I think now you are ready to start exploring advanced papers and also more established results. And I think this is therefore a good point to stop. Thank you.